Right now, a spacecraft is crossing the solar system to do something that has never been done. In nearly 70 years of spaceflight, we have orbited Mercury, Venus, Mars, even a comet, but never a moon. Not one, except our own. This mission is about to break that, and the target it picked tells you everything. It is heading for a moon wider than the planet Mercury, the only moon in the solar system that generates its own magnetic field, hiding a saltwater ocean 100 kilometers deep beneath its ice. You do not aim a multi-billion-dollar mission at a frozen rock. You aim it at a world. Its name is Ganymede, and by the end of this, the word moon is going to feel far too small for it. If deep dives that change how you see the solar system are your thing, like and subscribe, it truly helps this channel keep making them. Now, let's begin. Say the word moon out loud. Notice what your brain does. It conjures something small, something dependent, a pale, cratered companion trailing obediently behind a larger, more important object. The word moon carries a set of assumptions so deeply embedded in how people think about space that most of us never stop to examine them. Moons are supposed to be minor. Moons are supposed to be simple. Moons are supposed to be the supporting cast while planets hold the stage. And that mental picture works reasonably well for most of the moons in the solar system. Earth's moon is a battered grey sphere roughly 1/4 the diameter of our planet, geologically dead, airless, and entirely dependent on Earth's reflected sunlight to even be visible. It is the moon most humans think of first, and it is the reason the word carries the weight it does. Small, quiet, secondary. Now, forget everything you just imagined, because there is a moon orbiting Jupiter right now that is 5,268 kilometers across, that is wider than the planet Mercury by nearly 400 kilometers. It is 8% larger than Mercury in diameter and 26% larger in total volume. If you could peel Ganymede away from Jupiter's orbit and stand it beside Mercury in open space, the moon would visibly dwarf the planet. The object we call a moon would look like the larger world. The object we call a planet would look like the smaller companion. And that single image, a moon physically bigger than an actual planet, is where the idea of what a moon is supposed to be starts to crack. Ganymede is not slightly larger than you expect. It is so large that the comparison stops making intuitive sense. Its diameter stretches roughly 2/3 the width of Mars. Think about that for a moment. Mars fills entire documentaries. Mars dominates headlines about future human colonization. Mars is a planet people can name without hesitation, a world that feels significant and real in the public imagination. Ganymede measures roughly 66% of that planet's diameter. It sits in a size range that overlaps directly with objects the human mind treats as worlds, not accessories. And yet, the word we use for it is moon. The problem begins with how people learn about the solar system. Every classroom poster, every textbook diagram, every documentary animation presents the same basic hierarchy. The sun sits at the center. Planets orbit the sun in concentric paths. Moons orbit the planets. The hierarchy implies a ranking of importance. Planets are large, complex, and worth studying. Moons are small, simple, and worth mentioning only in the context of the planet they serve. This ranking is so intuitive that most people absorb it as a child and never revisit it. The word planet sounds like a destination. The word moon sounds like a footnote, but the solar system did not read the hierarchy we imposed on it. The solar system built Ganymede the same way it built planets. It differentiated its interior into layers. It generated a magnetic field from a liquid metallic core. It accumulated enough ice and rock to dwarf a planet. And then, because it happened to form inside Jupiter's gravitational well instead of in an independent orbit around the Sun, it got labelled with the smaller word. The label stuck. The object did not shrink to fit it. Let us be precise about the numbers, because precision is where the shock lives. Ganymede's mean radius is approximately 2,634 kilometers. Mercury's mean radius is approximately 2,440 kilometers. That gives Ganymede a diameter advantage of about 388 kilometers. To put that gap in perspective, the difference in their diameters is roughly the driving distance from Los Angeles to San Francisco. That is not a rounding error. That is a measurable, significant margin by which a moon exceeds a planet. Volume tells an even more dramatic story. Because volume scales with the cube of radius, a modest increase in diameter translates into a much larger increase in total size. Ganymede's volume exceeds Mercury's by approximately 26%. If you could hollow out Mercury and try to fit Ganymede inside it, roughly 1/4 of Ganymede would have nowhere to go. The moon does not fit inside the planet. The moon overflows the planet. Now, a careful observer will immediately raise an important objection. Mercury is far denser and far more massive than Ganymede. This is true, and it matters. Mercury's mass is roughly 2.2 times Ganymede's mass. Despite Mercury being the smaller object by diameter, Mercury is a ball of iron and rock compressed into a relatively compact sphere. It has an enormous metallic core that accounts for roughly 84% of the planet's radius, the largest core-to-body ratio in the entire solar system. Ganymede, by contrast, contains a significant fraction of water ice, which is far less dense than iron and silicate rock. Ganymede is a big object made partly of light material. Mercury is a smaller object made almost entirely of heavy material. This density difference is real and scientifically important. But here is why it does not rescue the mental category. When you look at a photograph of Ganymede and a photograph of Mercury side by side, your eyes do not see density. Your eyes see size. They see two spherical worlds, one clearly larger than the other. The larger one is the moon, and something in your brain protests. Because size is the first thing humans process when evaluating an object, and size is the metric on which Ganymede wins outright. Mass matters for physics. Diameter matters for perception. And perception is exactly where the idea of a moon breaks down. Consider how far Ganymede reaches beyond other objects most people would intuitively treat as significant. Pluto, the dwarf planet whose demotion from planetary status generated global controversy and genuine public grief, has a diameter of approximately 2,376 kilometers. Ganymede is more than twice Pluto's diameter. More than twice. The object that provoked a cultural crisis when it was stripped of the word planet would fit inside Ganymede with room to spare on every side. Yet nobody stages a protest for Ganymede. Nobody writes letters demanding it receive the title of planet. Because the word moon already sits on it like a lid, sealing it inside a category that prevents most people from ever registering its true scale. Ganymede also dwarfs every other moon in the solar system without exception. Titan, Saturn's largest moon and the second largest moon overall, comes closest with a diameter of approximately 5,150 kilometers. But even Titan falls over 100 kilometers short of Ganymede's width. Callisto, the third largest moon, sits at roughly 4,821 kilometers, noticeably smaller. Europa, the Galilean moon that dominates headlines about subsurface oceans and potential life, measures only 3,122 kilometers across, barely more than half Ganymede's size. Earth's own moon, the object that defines the entire category in the human mind, spans just 3,474 kilometers. Ganymede exceeds it by more than 1,700 kilometers. You could line up the diameter of Earth's moon, plus half of it again, and still not reach the far side of Ganymede. These are not abstract numbers. They represent the physical footprint of an object that sits in the wrong mental drawer. Every person who has ever looked up at the full moon and felt a sense of cosmic scale, every poet who treated it as a symbol of something vast and luminous, was looking at an object substantially smaller than a moon. They have likely never heard described in those terms, but the scale comparison becomes even stranger when you place Ganymede in the context of what orbits around it and what it orbits around. Ganymede circles Jupiter, the largest planet in the solar system, a gas giant so massive that it contains more matter than all other planets combined. Jupiter's diameter is roughly 143,000 kilometers. Ganymede's diameter is roughly 5,268 kilometers. That makes Ganymede approximately 3.7% of Jupiter's width. This ratio matters because it mirrors the relationship between other moons and their planets closely enough to feel ordinary. Earth's moon, for comparison, is roughly 27% of Earth's diameter, which is actually a much higher ratio. By that metric, Ganymede seems modest relative to its host, but the modesty is an illusion created by Jupiter's absurd size. Jupiter is so enormous that even a world larger than Mercury looks like a small companion orbiting it. The ratio tells you about Jupiter's dominance, not about Ganymede's insignificance. If Ganymede orbited a smaller planet, if it circled Mars or even Earth, it would not look like a moon. It would look like a collision partner. It would look like a second world locked in gravitational embrace with the first. The only reason Ganymede feels subordinate is that its host happens to be a monster. This is the first layer of the category collapse. Ganymede does not feel like a moon because its size places it firmly in the range of objects people treat as worlds. It exceeds a planet in diameter. It dwarfs a dwarf planet by a factor of 2. It towers over every other satellite in the solar system. And the only thing preventing the human mind from treating it as something grander is a single word applied to it because of where it orbits rather than what it is. There is another dimension to this that rarely gets discussed, and it involves how we experience objects at a distance versus how we would experience them up close. Mercury, the planet that Ganymede exceeds in size, has a surface gravity of approximately 3.7 meters per second squared. Ganymede's surface gravity is approximately 1.428 meters per second squared, much lower because of its lower density. If you stood on Mercury, you would weigh roughly 38% of what you weigh on Earth. If you stood on Ganymede, you would weigh roughly 14.5% of what you weigh on Earth. A person weighing 150 pounds on Earth would weigh 57 pounds on Mercury and about 22 pounds on Ganymede. That difference is dramatic and reflects the density gap between the two objects, but here is the perceptual detail that matters. If you stood on the surface of Ganymede and looked out toward the horizon, the curvature of the ground beneath your feet, the distance to the horizon line, and the sheer expanse of terrain stretching in every direction would feel planetary. Ganymede is large enough that standing on it would feel like standing on a world. The horizon would sit at roughly 3 kilometers distance, assuming a human eye height of about 1.7 meters. On Mercury, the horizon would sit at roughly 2.9 kilometers, slightly closer because Mercury's radius is smaller. The margin between them is modest but real, and it points the wrong direction for what the word moon implies. You would see farther on the moon than on the planet. The ground would curve less, the world would feel bigger. But the numbers alone do not capture what Ganymede would feel like as a place. So let us actually go there for a moment. Stand on the surface. Look around. Feel what this world is. The ground beneath your feet is ice. Not the thin, fragile ice of a frozen pond, but ancient ice compacted over billions of years under its own weight. Ice so old and so dense that it behaves more like rock than anything you would recognize from a winter landscape on Earth. The surface is grey, not white. Micrometeorite bombardment and radiation exposure have darkened and altered the ice over eons, giving it a texture that looks more like weathered stone than anything frozen. In the older regions, the terrain is cratered and battered, the scars of 4 billion years of impacts preserved in a surface too dead to erase them. But in the younger regions, the ground is carved with grooves, long parallel ridges and troughs that stretch toward the horizon and beyond, carved by tectonic forces that once cracked this ice shell from below. You are standing on terrain that was shaped by the interior of a world, not by external bombardment alone. The ground tells you that something underneath was once powerful enough to crack the surface open over thousands of kilometers. Now look up. The sun is there, but it is small. Ganymede orbits Jupiter at an average distance of roughly 778 million kilometers from the sun, more than 5 times the distance between Earth and the sun. In fact, at that distance, the sun appears roughly 1/27th as bright as it does from Earth. It is still the brightest object in the sky by far, still unmistakably a star, but it looks diminished, shrunken, a fierce white point of light that casts shadows but does not warm the ground. The surface temperature around you is approximately minus 163 degrees Celsius. The sun cannot help you here, but the real spectacle is not the sun. It is Jupiter. Depending on where you stand on Ganymede's surface and where the moon sits in its orbit, Jupiter dominates the sky in a way that no object dominates the sky from Earth. Ganymede orbits Jupiter at a distance of roughly 1,070,000 kilometers. From that distance, Jupiter's enormous disk spans roughly 8 degrees of arc in Ganymede's sky. For comparison, Earth's moon spans roughly half a degree in our sky. Jupiter, as seen from Ganymede, appears roughly 16 times wider than the full moon appears from Earth. It does not look like a point of light. It does not look like a dot. It hangs in the sky like a wall, a vast banded sphere of amber and white cloud belts, its great red spot a visible swirl of colour large enough to see with the naked eye. The planet fills your field of vision in a way that nothing in Earth's sky ever does. It is inescapable, overwhelming, a constant reminder that the world you are standing on belongs to something vastly larger. And yet the world you are standing on stretches to the horizon in every direction, slightly farther than you could see standing on the planet Mercury. The surface area beneath your feet exceeds that of Earth's largest continent. The ice beneath you conceals an ocean deeper than any abyss on Earth. The faint shimmer near the poles, if your eyes could see in ultraviolet, would reveal auroras generated by a magnetic field that no other moon in the solar system possesses. This is what standing on a moon feels like when the moon is Ganymede. It does not feel minor. It does not feel secondary. It feels like standing on a world that happens to have a larger world painted across its sky. This is a subtle but critical point. Scale shapes experience, and by the metric of surface experience, Ganymede would not feel like standing on a piece of debris trailing behind a larger body. It would feel like standing on a place, a location with geography, with a visible horizon that stretches beyond comfortable walking distance, with enough surface area that a person could spend an entire lifetime exploring and never see more than a fraction of the terrain. Ganymede's surface area is approximately 87 million square kilometers. That is larger than the surface area of Mercury, which sits at approximately 75 million square kilometers. It is also larger than the entire continent of Asia, the largest landmass on Earth. The Moon has more surface real estate than the planet it exceeds in diameter, and more habitable square footage than any single continent humans have ever mapped. The numbers keep compounding in the same direction. Every metric that describes spatial extent, diameter, volume, surface area, horizon distance, pushes Ganymede out of the mental category reserved for moons and into the category reserved for worlds. And every metric that pulls it back, mass, density, surface gravity, reflects only the fact that Ganymede is built from lighter materials than Mercury's iron-heavy core. The Moon is made of different stuff, not less stuff spatially. It simply weighs less per unit of volume because ice and silicate rock are lighter than compressed iron. But density has never been the axis along which human beings evaluate the significance of a celestial object. Nobody looks at Saturn, the least dense planet in the solar system, a planet that would technically float in a hypothetical bathtub large enough to hold it, and says Saturn is not a real planet because its density is lower than Earth's. Saturn is enormous. Its diameter is roughly 120,000 kilometers. Its density is beside the point because its spatial presence is overwhelming. The same logic applies to Ganymede. Its density is lower than Mercury's. Its spatial presence is larger than Mercury's. And spatial presence is what determines how a world feels. There is one more comparison that crystallizes the absurdity before we leave the subject of scale entirely. Imagine placing every named dwarf planet in the solar system side by side. Pluto, at roughly 2,376 kilometers in diameter. Eris, at approximately 2,326 kilometers. Haumea, at roughly 1,632 kilometers in mean diameter. Marke, at approximately 1,430 kilometers. Ceres at roughly 946 kilometers. Every single one of these objects received a distinct classification because the astronomical community decided they were significant enough to discuss individually. Every single one of them is smaller than Ganymede by a wide margin. Ganymede exceeds the largest of them, Pluto, by nearly 3,000 kilometers in diameter. It exceeds the smallest, Ceres, by more than 4,300 kilometers. These objects triggered classification debates that consumed international astronomical conferences for years. Ganymede triggered nothing. It sat quietly in its orbit around Jupiter, filed under the word moon, and stayed there. The word moon, when applied to Ganymede, is not technically wrong, it is gravitationally correct. Ganymede orbits Jupiter. Jupiter orbits the Sun. By the standard definition, any natural object orbiting a planet rather than a star is a moon. Ganymede satisfies this definition cleanly. There is no taxonomic argument to be made that Ganymede is secretly a planet or has been misclassified. The International Astronomical Union does not need to hold an emergency vote. Ganymede is a moon, but that is precisely what makes it so unsettling. The definition is doing real work to keep an object larger than a planet inside a category that most people associate with something far smaller and far less significant. The definition is technically accurate and emotionally misleading at the same time. Ganymede is a moon, the way a great white shark is a fish. The classification is correct. The mental image it produces is catastrophically wrong. And this brings us to the edge of something deeper, because the size of Ganymede is not actually the most disturbing thing about it. The most disturbing thing about Ganymede is what that size enabled. An object this large had enough internal heat, enough gravitational pressure, and enough raw material to develop an interior that does not look like a moon's interior at all. It looks like the interior of a planet. Ganymede did not just grow large, it grew complex. It separated into layers, it built a metallic core, it generated a magnetic field that no other moon in the solar system has ever managed to produce. It accumulated enough ice to bury a saltwater ocean so deep and so vast that it may contain more liquid water than every ocean on Earth combined. Size broke the intuition, but what happened inside Ganymede is what breaks the category entirely, and that story begins beneath 150 kilometers of ancient ice. Most moons in the solar system are, for lack of a gentler description, lumps, cold, undifferentiated masses of rock and ice that never accumulated enough heat or pressure to reorganize their interiors into anything structured. They formed, they cooled, and they stayed more or less the same from the outside in. A chunk of material orbiting a planet, homogeneous and geologically inert, doing nothing internally except sitting there. This is the default state for a moon. This is what the word implies when scientists use it casually. A companion object that never developed the internal machinery to become anything more complex than the raw ingredients it started with. Ganymede refused. Beneath the frozen surface of this moon lies an interior so structured, so layered, so thermally active that it mirrors the architecture found inside rocky planets. Ganymede is not a lump, it is a differentiated world. And that single word, differentiated, represents the dividing line between an object that remained geologically primitive and an object that cooked itself into something organized. Differentiation means that at some point in Ganymede's history, the interior grew hot enough for materials of different densities to separate. Heavy elements like iron sank toward the center. Lighter silicate rock settled above the iron, and the lightest material, water ice, rose to the top and formed a thick outer shell. The result is a layered structure that, if you sliced Ganymede in half and looked at the cross-section, would resemble a textbook diagram of a terrestrial planet. At the very center sits an iron and iron sulfide core. This core is not a cold, dead ball of solidified metal. Evidence strongly indicates that at least part of it remains liquid. The core's estimated radius falls somewhere between roughly 400 and 1,300 kilometers, depending on the model, with most current estimates placing the iron-rich inner region at roughly 500 to 800 kilometers across. Surrounding this metallic heart is a silicate mantle, a thick shell of rocky material, similar in composition to the rocky mantles found inside Earth and Mars. And above the mantle sits the feature that dominates Ganymede's outer structure, an ice shell so deep and so massive that it extends roughly 800 kilometers from the mantle boundary to the surface. 800 kilometers of ice and water in various phases, stacked in layers, encasing the rocky interior like a frozen suit of armor. This structure did not assemble itself by accident. It required energy, enormous amounts of energy, sustained over geological time, to heat the interior enough for gravitational separation to occur. Where did that energy come from? Several sources contributed. The original accretion process, when material collided and compressed to form Ganymede roughly 4.5 billion years ago, generated significant heat through impact energy. Radioactive decay of elements like potassium, uranium, and thorium within the rocky material provided a slow but steady internal heat source over billions of years. And tidal interactions with Jupiter, the constant gravitational flexing that Ganymede experiences as it orbits the most massive planet in the solar system, added additional thermal energy to the interior over time. Together, these heat sources were sufficient to melt and reorganize the interior into the layered structure scientists observe today. The tidal energy deserves closer attention because it connects Ganymede to two of its nearest neighbors in a way that has shaped all three worlds for billions of years. Ganymede does not orbit Jupiter alone. It shares the Jovian system with Io, the innermost of the four large Galilean moons, and Europa, which orbits between Io and Ganymede. These three moons are locked in a gravitational arrangement known as the Laplace resonance, a precise orbital relationship in which Io completes exactly 4 orbits around Jupiter. For every 2 orbits Europa completes, and Europa completes exactly 2 orbits for every single orbit Ganymede completes. The ratio is 4 to 2 to 1, maintained continuously by the gravitational tugging the 3 moons exert on one another every time they align. This resonance is not a coincidence or a temporary arrangement. It is a stable, self-reinforcing system that has persisted for a significant fraction of solar system history, and it has consequences. The resonance prevents the orbits of all 3 moons from becoming perfectly circular. Each moon's orbit retains a slight eccentricity, a mild elongation that means the distance between the moon and Jupiter changes over the course of every orbit. That changing distance means the strength of Jupiter's gravitational pull on each moon fluctuates rhythmically. The fluctuation flexes the moon's interior, compressing and stretching it slightly with every orbital cycle. This flexing generates friction inside the moon, and friction generates heat. For Io, the innermost moon, this tidal heating is catastrophically intense. Io is the most volcanically active body in the solar system, with hundreds of active volcanoes driven by the relentless squeezing of Jupiter's gravity, amplified by the resonance. For Europa, the heating is more moderate but still significant, enough to maintain a liquid water ocean beneath a thin ice shell. For Ganymede, the outermost member of the resonance and the farthest from Jupiter, the tidal heating is the gentlest of the 3. But gentle does not mean negligible. Over billions of years, even modest tidal energy supplements the heat from radioactive decay and accretional energy, contributing to the thermal budget that allowed Ganymede to differentiate fully, and that may continue to sustain liquid water and core activity today. The resonance also means that Ganymede's geological history is not independent of its neighbours. The 3 moons evolved together, their internal heat budgets linked by the same orbital mechanism. What happened inside Io, the extreme volcanic case, what happened inside Europa, the thin ice ocean case, and what happened inside Ganymede, the thick ice differentiated case, are all variations on a single gravitational theme. Jupiter built an engine out of orbital mechanics, and that engine has been driving the internal evolution of 3 separate worlds for billions of years. Each world responded differently based on its distance from Jupiter, its size, and its composition, but all 3 owe their internal activity, in part, to the resonance they share. Differentiation is not unique to Ganymede among moons. Europa and Io, 2 of Ganymede's fellow Galilean satellites, are also differentiated to varying degrees, but Ganymede's differentiation is the most complete and the most planet-like. Its layered interior with a metallic core, a silicate mantle, and an icy outer shell mirrors the basic architecture of Earth more closely than almost any other body in the outer solar system. The only thing missing from the comparison is a thin atmosphere and liquid water on the surface. And as it turns out, Ganymede has a version of both, just not the kind visible to the naked eye. But the interior structure is not the feature that makes Ganymede unique among every moon in the solar system. That distinction belongs to something far stranger. Something that, when scientists first detected it, forced them to fundamentally rethink what a moon was capable of producing. Ganymede has its own magnetic field, not an induced field borrowed from Jupiter's overwhelming magnetosphere, not a residual trace of ancient magnetism frozen into surface rocks. A present-tense, actively generated, intrinsic magnetic field, produced by dynamo action in its liquid metallic core. The same fundamental mechanism that produces Earth's magnetic field, the same process that gives Mercury, Jupiter, Saturn, Uranus, and Neptune their magnetic shields. The same physics that requires a liquid, electrically conducting interior, churning with enough vigor to convert kinetic energy into magnetic energy through convection and rotation. Out of more than 300 known moons in the solar system, Ganymede is the only one that does this. Not one of a handful, not one of several candidates. The only one. Every other moon, from Titan to Europa to Triton to Earth's own moon, either never generated an intrinsic magnetic field or generated one in the ancient past and lost it as its core cooled and solidified. Ganymede alone maintains an active dynamo right now, today. As you listen to these words, its metallic core is still liquid, still convecting, still producing a magnetic field that carves out a distinct magnetosphere entirely embedded within Jupiter's own vastly larger magnetic environment. The discovery happened during a mission that was not specifically looking for it. In the mid-1990s, NASA's Galileo spacecraft was orbiting Jupiter and conducting a systematic survey of the Jovian system. The spacecraft carried a magnetometer, an instrument designed to measure the strength and direction of magnetic fields in the environment around Jupiter and its moons. On June 27, 1996, Galileo made its first close flyby of Ganymede, passing within roughly 840 kilometers of the surface. The magnetometer recorded something that the science team did not initially expect. As the spacecraft approached Ganymede, the magnetic readings began deviating from the pattern predicted by Jupiter's field alone. There was an additional signal, a coherent magnetic signature that strengthened as Galileo drew closer to the moon and weakened as it pulled away. The pattern was consistent with a dipolar magnetic field originating from inside Ganymede itself. The team ran the numbers. They modelled Jupiter's magnetic field at Ganymede's orbital position and subtracted it from the observed data. What remained was unmistakable. Ganymede was generating its own field. The equatorial surface strength measured roughly 750 nanotesla. The polar strength reached roughly 1,200 nanotesla. These values were modest compared to Earth's field, which averages roughly 25,000 to 65,000 nanotesla at the surface, but they were far too strong and far too organized to be explained by any mechanism other than an active internal dynamo. The announcement sent a tremor through planetary science. Moons were not supposed to do this. The conventional understanding held that an object needed to be large enough and hot enough to maintain a liquid metallic core capable of sustained convection. Earth could do it. The giant planets could do it. Mercury barely could do it. But a moon, even a large one, was expected to have cooled too much over 4.5 billion years to keep this process running. The textbook said no. Ganymede said otherwise. And subsequent Galileo flybys in 1996 and 1997 confirmed the initial detection beyond any reasonable doubt. The immediate question was obvious. How is Ganymede still doing this? Magnetic dynamos require sustained energy input to keep the core convecting. Earth's dynamo is powered primarily by the slow crystallization of its inner core, which releases latent heat and drives convective currents in the liquid outer core. But Ganymede is far smaller than Earth. Smaller objects cool faster. A body Ganymede's size should have lost enough internal heat over 4.5 billion years for its core to solidify, or at least become too sluggish to maintain dynamo action. Mars, which is physically larger than Ganymede, lost its global magnetic field billions of years ago as its core cooled. Why does Ganymede still have one? This question nagged planetary scientists for decades. Various explanations were proposed. Tidal heating from Jupiter's gravitational influence, amplified by the Laplace resonance with Io and Europa, could provide supplemental energy to keep the interior warm. The composition of the core, if it contains a significant fraction of sulfur in the form of iron sulfide, would lower the melting point and allow the core to remain partially liquid at lower temperatures than a pure iron core would require. The iron sulfide hypothesis is particularly important because sulfur acts as a kind of antifreeze for metallic cores. A core that would solidify at a certain temperature if it were pure iron can remain liquid hundreds of degrees below that threshold if it contains enough sulfur. This would extend the window during which dynamo action is possible, potentially stretching it across the full age of the solar system. But none of these explanations, individually or combined, fully resolved the puzzle of how an object this size sustains an active dynamo after billions of years. The tidal heating helps, but may not be sufficient on its own. The sulfur content extends the liquid phase but does not eliminate the cooling problem entirely. Something else seemed to be happening inside Ganymede, something that the standard thermal evolution models were not capturing. Then, in 2026, a study led by Kevin Trin at Arizona State University proposed a new explanation that reframes the entire problem. Published in the journal Science Advances, the research suggests that Ganymede's dynamo may not be powered by the conventional cooling of an already formed core. Instead, the magnetic field may be sustained by ongoing core formation itself. The idea is that Ganymede's interior may still be gradually separating. Iron and iron sulfide material may still be slowly sinking from the mantle into the core, releasing gravitational energy and generating convective motion as it descends. Rather than a fully formed core that is slowly cooling down, Ganymede may have a core that is still being built, still accreting dense material, still stirring itself through the very process of assembly. This model flips the conventional timeline. Instead of asking why Ganymede's core has not yet cooled enough to shut down, it asks whether the core has even finished forming. Radioactive decay, gravitational energy from ongoing differentiation, and tidal heating from Jupiter may together maintain enough internal warmth to keep the separation process active. Dense metallic material continues settling inward. The motion stirs the liquid core. The stirring produces the dynamo. The dynamo produces the magnetic field, and the magnetic field produces something that no one expected to find on a moon. Auroras. Ganymede has auroras, ribbons of glowing electrified gas circling both poles, generated by the interaction between the moon's own magnetic field and the charged particles trapped in Jupiter's immense magnetosphere. These are not faint theoretical signatures buried in data. These are visible features observed directly by the Hubble Space Telescope, glowing in ultraviolet wavelengths, rocking gently back and forth as Jupiter's magnetic field tugs on Ganymede's smaller field from the outside. Auroras on a moon, produced by the moon's own internal magnetic engine. The only moon in the solar system where this happens. The auroras exist because Ganymede's magnetosphere, though small, creates a genuine boundary with the surrounding Jovian magnetic environment. Charged particles streaming through Jupiter's magnetosphere encounter this boundary and are funneled along Ganymede's field lines toward the poles, where they collide with the thin oxygen exosphere that clings to the moon's surface. Those collisions excite oxygen molecules, which release energy in the form of ultraviolet light. The result is a pair of auroral ovals, one in each hemisphere, glowing faintly but persistently against the frozen surface below. These ovals are not static. They shift position as Jupiter's magnetic field rotates and changes orientation relative to Ganymede. The auroras rock back and forth around the poles, responding to the external magnetic pressure, like a compass needle nudged by a passing magnet. And those auroras became the key that unlocked another secret hidden beneath the ice. In 2010 and 2011, a team led by Joachim Sauer at the University of Cologne in Germany used Hubble to study the motion of Ganymede's auroral belts in detail. The physics is elegant and worth understanding carefully, because the method itself represents one of the most creative acts of remote sensing in modern astronomy. Jupiter's enormous magnetic field rotates with the planet and periodically shifts orientation relative to Ganymede. This external field change exerts a force on Ganymede's own magnetic field, which should cause the auroral ovals to rock back and forth around the poles by approximately 6 degrees. That 6-degree prediction comes from modelling how Ganymede's magnetic field should respond to Jupiter's influence if the moon's interior were entirely solid ice and rock below the surface. In a completely frozen Ganymede, nothing would resist the external push. The auroras would rock the full predicted amount. But when the team measured the actual rocking motion across multiple Hubble observation sessions spanning 7 hours of Jupiter's rotation, the auroras shifted by only about 2 degrees. Something inside Ganymede was resisting Jupiter's magnetic influence, damping the oscillation, fighting back against the external field. The suppression was significant. 2/3 of the expected motion was being absorbed by something beneath the surface. The explanation required a layer of electrically conductive material between the surface ice and the deeper interior. Saltwater, a deep, briny ocean conducting enough electrical current to generate a secondary magnetic field that partially cancels Jupiter's influence on Ganymede's auroras. When Jupiter's field pushes on Ganymede, the changing magnetic flux induces currents in the conductive ocean. Those currents produce their own magnetic field pointing in the opposite direction, counteracting the external push. The result is a dampened auroral wobble, exactly the signature SOUR's team observed. The method is remarkable for what it accomplished without ever touching the moon. No probe drilled through the ice. No seismometer listened for subsurface liquid. No lander sampled the surface. A telescope orbiting Earth watched lights flickering at the poles of a moon orbiting Jupiter, measured how much those lights moved, compared the motion to a theoretical prediction, and concluded that a massive body of saltwater must exist beneath the ice to explain the difference. The suppressed rocking motion was the signature of a subsurface ocean, detected purely through the physics of magnetic induction observed from roughly 628 million kilometers away. NASA described the finding as the best evidence yet for an underground ocean on Ganymede. The estimated parameters of this ocean are staggering. Scientists calculate that the liquid water layer sits approximately 150 kilometers beneath the surface, buried under a thick crust of solid ice. The ocean itself is estimated to be roughly 100 kilometers deep. 100 kilometers. For comparison, the average depth of Earth's oceans is approximately 3.7 kilometers. The deepest point on Earth, the bottom of the Mariana Trench, reaches roughly 11 kilometers. Ganymede's ocean, if the estimates are correct, is approximately 10 times deeper than the deepest point on Earth and roughly 27 times deeper than Earth's average ocean depth, and it extends around the entire moon. The total volume of water may exceed the combined volume of every ocean on Earth's surface. This ocean is not sitting in an open basin exposed to sunlight. It is sealed beneath a shell of ice so thick that no surface feature betrays its presence directly. The water exists under enormous pressure, sandwiched between ice above and potentially more exotic high-pressure ice phases below. Some models suggest Ganymede's ice and water shell may contain multiple layers, a stacked structure of ice and liquid water alternating at different depths, like a geological layer cake made of frozen and melted water in different crystalline states. Water ice, under extreme pressure, can transition into exotic forms with names like Ice 3, Ice 5, and Ice 6, each with a different crystal structure and density. At the pressures found deep within Ganymede's 800-kilometer ice shell, some of these high-pressure ice phases are denser than liquid water and could form solid layers beneath the ocean rather than above it. The lowest liquid layer may sit directly on top of the silicate mantle, where rock meets water in conditions that could theoretically drive chemical reactions relevant to the question of habitability. But that question comes later. What matters right now is what the ocean represents for the mental category. Ganymede is not a frozen, dead ball of ice orbiting Jupiter. It is a world with a liquid interior. It has a metallic core generating a magnetic field. It has a rocky mantle providing the structural backbone. It has a deep ocean containing more liquid water than the entire surface of the planet where humans evolved. And it has an ice shell thick enough to seal all of this away from view, hiding a world-scale hydrosphere beneath a surface that looks, at first glance, like nothing more than old, grey, cratered ice. The surface itself carries clues about what lies beneath, and those clues are more dramatic than most people realize. Ganymede's terrain divides broadly into two categories that tell two very different stories about the moon's geological history. Roughly 1/3 of the surface consists of ancient, dark, heavily cratered regions that date back roughly 4 billion years. These dark terrains record the heavy bombardment period early in solar system history, when debris left over from planetary formation rained down on every surface in the inner and outer solar system. The craters in these regions are dense, overlapping, and largely unchanged since they formed. They represent Ganymede's oldest surviving surface, a geological record frozen in time. The remaining 2/3 of the surface tells a completely different story. This terrain is younger, brighter, and dominated by an extraordinary system of grooves, ridges, troughs, and fractures that stretch across the moon's face in complex interlocking patterns. Some groove systems extend for thousands of kilometers, carving parallel lines into the ice like the marks of an enormous comb drawn across a frozen plain. The grooves vary in width from a few hundred meters to several kilometers, and in depth from tens of meters to hundreds. They cut through older, cratered terrain, overwriting the ancient surface with evidence of forces that came from below. This grooved terrain did not form by impact, it formed by tectonics. Internal stresses propagated outward through the ice shell, cracking and deforming the surface in patterns that record the strain. The forces that created these grooves originated deep inside Ganymede, likely driven by the same heat sources that powered differentiation and that maintain the subsurface ocean. The ice shell, hundreds of kilometers thick, behaved as a geological medium, capable of transmitting stress over vast distances and fracturing in organized patterns rather than random cracks. In some regions, the grooved terrain shows evidence of extensional tectonics, where the surface was pulled apart and new material filled the gaps. In other regions, the patterns suggest strike-slip faulting, where blocks of ice slid past one another horizontally. The complexity of these tectonic features approaches the complexity seen on geologically active bodies like Earth and Europa. No simple, dead moon produces terrain like this. Grooved terrain requires energy. It requires internal stress propagating outward through an ice shell thick enough to behave like a geological medium. It requires a world that was doing something beneath its surface, something vigorous enough to crack ice over thousands of kilometers. And the grooves do not all date to the same era. Some are older, more degraded, partially overprinted by later features. Others appear fresher, sharper, less eroded by micrometeorite bombardment. This variation in apparent age suggests that Ganymede's tectonic activity was not a single event. It was a process, recurring over an extended period of geological time, possibly spanning hundreds of millions of years or more. The question of whether any tectonic activity continues today remains open. The grooved terrain could represent an ancient episode that has since ended, or it could represent the most recent visible evidence of processes that continue at a slower pace beneath the surface. The evidence suggests that something may still be happening. In 2021, NASA's Juno spacecraft performed a close flyby of Ganymede, passing within approximately 1,046 kilometers of the surface. The onboard Jovian infrared auroral mapper, referred to as JIRAM, captured infrared images and spectra of the surface with unprecedented spatial resolution, better than 1 kilometer per pixel. At that resolution, individual geological features became distinguishable for the first time in infrared wavelengths. The findings, published in the journal Nature Astronomy in 2023, revealed mineral salts and organic compounds on Ganymede's surface. Specifically, the instrument detected signatures consistent with hydrated sodium chloride, ammonium chloride, sodium and ammonium carbonates, and organic molecules that may include aliphatic aldehydes. The presence of ammoniated salts carries its own significance. Ammonia is a volatile compound that condenses only at very low temperatures, which suggests that Ganymede may have accumulated materials from the cold outer reaches of the solar nebula during its formation. This places constraints on where and how Ganymede assembled itself billions of years ago, linking its surface chemistry to the conditions of its birth. But the location of these deposits is what makes the findings truly compelling. The greatest concentrations of salts and organics appeared in terrain at latitudes protected by Ganymede's magnetic field, regions where Jupiter's intense radiation bombardment is partially deflected. Jupiter's magnetosphere is a brutal environment. Charged particles accelerated to enormous energies stream through the Jovian system, bombarding the surfaces of the inner moons with radiation intense enough to break apart complex molecules. At Ganymede's equatorial and mid-latitudes, where the moon's own magnetic field creates a magnetopause that deflects some of this radiation, delicate chemical compounds have a chance of surviving on the surface. At higher latitudes, outside the magnetic shield, those same compounds would be destroyed. The fact that salts and organics survive in magnetically protected zones but not in unshielded regions, suggests they are being replenished, not merely ancient relics frozen in place since the solar system's early days. If these compounds were primordial, deposited during Ganymede's formation and never refreshed, they would have been destroyed everywhere on the surface by now, including in the magnetically shielded zones. Billions of years of even modest radiation exposure would have erased them. Their survival implies a source that is ongoing, a mechanism that continues to deliver fresh material to the surface from somewhere below. Scott Bolton, Juno's principal investigator, described the findings directly. The salts and organics appear to be remnants of deep ocean brine that reach the surface of this frozen world. Think about what that sentence means. Material from the interior ocean, carrying dissolved salts and organic chemistry, may have migrated upward through the ice shell and reached the surface. The ocean is not perfectly sealed. It leaks. Briny water, carrying the chemical fingerprint of a deep, salty, potentially chemically active ocean, finds pathways through 150 kilometers of ice and deposits evidence of its existence on the ground above. The mechanism for this migration is not fully understood, but several possibilities exist. Warm ice from the lower shell could rise through convective plumes, carrying dissolved material upward. Fractures in the ice could provide conduits for liquid or semi-liquid brine to migrate toward the surface. Tidal stresses from Jupiter could periodically open and close pathways that allow material exchange between the ocean and the surface. A 2026 study further strengthened this picture by identifying candidate cryovolcanic regions on Ganymede's surface. Using data from the Galileo mission, an international research team led by scientists at the Hellenic Space Center identified several features called paterae, collapse-like depressions that may act as vents, where subsurface water and volatile compounds escape to the surface. These features, if confirmed by future observation, would mean Ganymede is not just hiding an ocean, it is actively communicating between its deep interior and its outer surface through geological processes that transport material across the entire thickness of the ice shell. The ocean would not merely exist. It would express itself on the surface, leaving chemical fingerprints that spacecraft can detect and sample. Every element of this interior picture points in the same direction. The differentiated layering, the active magnetic dynamo powered by a core that may still be forming, the deep saltwater ocean with potentially more water than Earth, the surface salts and organics suggesting brine migration from ocean to ice, the grooved terrain recording ancient tectonic activity driven by internal forces, the auroras confirming a functioning magnetosphere, the orbital resonance with Europa and Io providing sustained tidal energy across billions of years. Each feature alone would be noteworthy on any body in the solar system. Combined in a single object, they describe something that does not match what the word moon is supposed to contain. Earth is a differentiated world with a metallic core, a silicate mantle, liquid water, a magnetic field, auroras, and surface evidence of geological activity driven by internal processes. Nobody hesitates to call Earth a planet. Ganymede possesses a version of every single one of those features, scaled down in magnitude but structurally identical in kind. And yet the word applied to it implies something closer to a dead rock trailing behind a planet than to a world operating its own geological machinery. The machinery is real, the core is liquid, the dynamo is active, the ocean is deep, the surface is marked by processes that originate hundreds of kilometers below, and the entire system, this engine inside the ice, has been running for billions of years quietly, invisibly, inside an object that most people have never even heard described as anything other than one of Jupiter's moons. But Ganymede does not exist in isolation. No, it orbits alongside other moons, beneath the shadow of a planet, within a broader solar system full of objects that carry the same categorical label. And when you line Ganymede up against those objects, when you compare it feature by feature against the planet it exceeds in diameter and the moons it shares a classification with, the results are not subtle. They are embarrassing, not for Ganymede, but for the idea that a single word can meaningfully contain objects this different from one another. There is a test that clarifies how badly the word moon fails when applied to Ganymede. The test is simple. Take everything scientists know about Ganymede and everything they know about Mercury. Strip away the names. Strip away the orbital context. Present both objects as anonymous worlds described only by their physical properties, their internal structure, their surface features, and their active processes. Then ask someone to guess which one is the planet. They will guess wrong. Mercury is a world defined primarily by what it lacks. It has no substantial atmosphere. The thin exosphere clinging to its surface contains traces of sodium, oxygen, hydrogen, and helium, but the gas density is so negligible that molecules almost never collide with one another. By any functional definition, Mercury is airless. Its surface is exposed directly to the vacuum of space, baked by the sun on the day side, to temperatures exceeding 430 degrees Celsius, and frozen on the night side to roughly minus 180 degrees Celsius. There is no weather, no wind, no erosion by gas or liquid. The craters that pockmark Mercury's surface have remained essentially unchanged for billions of years because nothing exists on the surface to wear them away. Mercury has no moons of its own. No natural satellite of any size orbits this planet. In the hierarchy of gravitational companionship, Mercury stands alone, a planet so solitary that it cannot even claim the kind of gravitational relationship that defines Ganymede's existence. Ganymede is a moon that has more world-like features than Mercury. Mercury is a planet that has fewer companions than most moons. Mercury does possess a magnetic field, and this is often cited as evidence of its planetary complexity. The field was confirmed by the Mariner 10 spacecraft in 1974, and later studied in extensive detail by NASA's Messenger mission, which orbited Mercury from 2011 to 2015. But Mercury's magnetic field is remarkably weak. Its surface strength measures roughly 1% of Earth's magnetic field strength. The field is strong enough to carve out a small magnetosphere that deflects some portion of the solar wind, but it is a feeble shield compared to Earth's protective magnetic envelope. Scientists believe Mercury's field is generated by a dynamo in its partially liquid core, but the dynamo appears to operate at low intensity, producing a field so modest that it barely holds its own against the relentless pressure of charged particles streaming from the sun. Now compare that to Ganymede. Ganymede's magnetic field, while weaker than Earth's in absolute terms, is strong enough to create its own distinct magnetosphere entirely embedded within Jupiter's far larger magnetic environment. Ganymede's field has equatorial surface strength of roughly 750 nanotesla and polar strength of roughly 1,200 nanotesla. Mercury's field strength at the equator measures roughly 300 nanotesla. Ganymede's magnetic field is more than twice as strong as Mercury's at comparable locations. A moon has a stronger magnetic field than a planet. This fact alone should cause discomfort in anyone who assumes the word planet automatically implies greater physical sophistication. The comparison deepens when you examine internal structure. Mercury's interior is dominated by its enormous iron core, which extends roughly 84% of the planet's radius. This gives Mercury the most extreme core-to-body ratio in the solar system. The core is partially liquid, allowing the weak dynamo to operate, but the silicate mantle above it is thin, only roughly 400 to 500 kilometers thick. Mercury is essentially a giant iron ball with a thin rocky wrapper. Its geological activity is minimal in the present era. There is evidence that Mercury experienced volcanic activity in its deep past, with lava plains called smooth plains covering roughly 27% of the surface. But those volcanic processes appear to have ceased billions of years ago. Mercury's most dramatic geological feature is the Callisto Basin, one of the largest impact structures in the solar system. The basin spans roughly 1,550 kilometers in diameter. Carved by an asteroid impact approximately 3.9 billion years ago, the collision was so violent that it sent shockwaves through Mercury's entire body. On the exact opposite side of the planet from the impact site, the focused seismic energy created a region of jumbled, chaotic terrain called the Weird Terrain, hills and depressions formed by the converging shockwaves that travelled through the planet and met on the far side. The Callisto Basin is geologically spectacular, but it is also ancient. The impact happened nearly 4 billion years ago. The basin has sat essentially unchanged since then, slowly accumulating small craters from minor impacts, its lava-filled floor cooling and cracking as Mercury's interior contracted over eons. That contraction tells its own story. As Mercury's iron core slowly cooled and solidified over billions of years, the planet shrank. The surface, forced to accommodate a smaller interior, buckled and compressed, producing long cliff faces called lobate scarps that stretch across the surface for hundreds of kilometers. Some of these scarps rise over a kilometer above the surrounding terrain. They are evidence of a planet tightening, contracting, its most dynamic geological days long behind it. Mercury's story is one of early intensity followed by billions of years of quiet. The planet finished its primary geological narrative in the deep past and has been essentially static ever since. Ganymede's interior, by contrast, is actively doing something right now. Its metallic core is liquid and convecting, generating a magnetic dynamo. Its ice shell preserves evidence of tectonic activity in the form of grooved terrain that covers roughly 2/3 of the surface. Its subsurface ocean may still be interacting with the ice shell above and the rocky mantle below, transporting salts and organic compounds toward the surface through processes that leave detectable chemical signatures. A 2026 study suggests the core may still be forming, with dense material continuing to separate from the mantle and sink inward, providing ongoing energy to sustain the dynamo. Mercury finished its primary geological story billions of years ago. Ganymede's geological story appears to still be in progress. Mercury has no water in any meaningful quantity. Trace amounts of water ice exist in permanently shadowed craters near Mercury's poles, where temperatures remain cold enough for ice to persist despite the planet's proximity to the Sun. These ice deposits were confirmed by MESSENGER's neutron spectrometer, and are scientifically interesting as evidence of volatile delivery to the inner solar system. But volumetrically, they are negligible. They amount to thin layers of frost hiding in shadows, perhaps a few meters thick at most, nothing resembling a hydrosphere. Ganymede, by contrast, is a water world. Its ice shell is roughly 800 kilometers thick. Its subsurface ocean is estimated at 100 kilometers deep, and may contain more liquid water than every ocean on Earth's surface combined. The difference is not marginal. It is categorical. Mercury is one of the driest objects in the inner solar system. Ganymede may be one of the wettest objects anywhere. Mercury has no known geological features suggesting present-day internal activity that reaches the surface. No geysers, no cryovolcanism, no eruptions. No active tectonics producing visible surface deformation in the current era. Ganymede has candidate cryovolcanic features, surface regions identified in 2026 as potential vents where subsurface water and volatiles may reach the surface. These features have not yet been confirmed by direct observation, but their identification adds Ganymede to a short list of solar system bodies suspected of active surface interior communication. If confirmed, Ganymede would join Enceladus, Io, and possibly Europa as worlds where internal processes visibly affect the surface in the present day. So, line up the scorecard. Magnetic field strength at the surface, Ganymede wins. Active internal dynamo, both have one, but Ganymede's may be powered by a process, ongoing core formation, that is more dynamically interesting than Mercury's slowly cooling remnant. Subsurface liquid water. Ganymede has a global ocean, potentially 100 kilometers deep. Mercury has traces of polar frost. Present-day geological activity. Ganymede shows strong evidence and active candidates. Mercury shows essentially none in the current epoch. Atmospheric presence. Both have only exospheres too thin to constitute real atmospheres, so this category is roughly a tie. Moons. Mercury has 0. Ganymede does not orbit anything smaller than itself, so this category does not apply in the same way. But it is worth noting that a planet has no companions, while a moon has planet-like complexity. Mercury wins on mass, density, proximity to the Sun, and historical pedigree as a planet known to ancient civilizations. These are real and important distinctions. Mass determines gravitational influence. Density reflects composition. Orbital context determines classification. Nobody is arguing that Mercury should be demoted or that Ganymede should be promoted. The taxonomy is what it is, but the feature-by-feature comparison reveals something that taxonomy alone cannot express. Ganymede is a more physically active, more structurally complex, more hydrologically rich, and more magnetically dynamic object than the planet it exceeds in diameter. The Moon is doing more than the planet. The Moon is more alive. Now turn the comparison in the other direction. How does Ganymede measure against the other major moons of the solar system? Titan, Saturn's largest moon and the second largest moon overall, is the object most often mentioned alongside Ganymede in conversations about planet-like moons. Titan has a thick nitrogen atmosphere with surface pressure roughly 50% higher than Earth's sea-level atmospheric pressure. It has lakes and seas of liquid methane and ethane on its surface, making it the only body in the solar system besides Earth with stable liquid on its surface in the present day. It has complex organic chemistry driven by ultraviolet photolysis in the upper atmosphere, producing a haze of hydrocarbon molecules that gives the Moon its characteristic orange appearance. The Cassini-Huygens mission, which studied Saturn's system from 2004 through 2017, revealed Titan to be a world of startling complexity, with rain cycles, river channels, dune fields, and seasonal weather patterns driven by methane rather than water. Titan is extraordinary, but Titan lacks something Ganymede has. Titan does not generate its own magnetic field. Despite being slightly larger in apparent diameter when its atmosphere is included, Titan produces no intrinsic magnetosphere. Saturn's magnetic field interacts with Titan's atmosphere directly, creating an induced magnetic environment rather than a self-generated one. Titan's interior, while likely containing a subsurface water-ammonia ocean, does not appear to drive a core dynamo. Whatever is happening inside Titan, it is not producing the organized magnetic output that Ganymede's core delivers. In the specific category of magnetic self-sufficiency, Ganymede stands alone among all moons everywhere. Europa, the Galilean moon that dominates public imagination when it comes to ocean worlds and the search for life, is smaller than Ganymede by a dramatic margin. Europa's diameter of roughly 3,122 kilometers makes it barely 60% of Ganymede's width. Europa's ice shell is thinner, possibly only 10 to 30 kilometers thick in some models, which means its subsurface ocean may be closer to the surface and potentially more accessible to future exploration. Europa's ocean is strongly suspected to be in direct contact with a rocky seafloor, which could drive hydrothermal chemistry relevant to biology. These features make Europa a compelling target for astrobiology. But Europa does not have an intrinsic magnetic field. It has no dynamo. Its interior is likely differentiated but does not produce the organized magnetic signature that Ganymede generates. Europa is a world defined by its ocean and the tantalizing possibility of life within it. Ganymede is a world defined by the sheer breadth of its planet-like features operating simultaneously. Size, layered interior, active dynamo, magnetic field, vast ocean, surface chemistry, and geological complexity. Europa excels in one dimension, Ganymede excels across many. Callisto, the outermost Galilean moon, sits in an interesting contrast with Ganymede, and this contrast may be the most scientifically instructive comparison available anywhere in the solar system. The two moons are similar in size, with Callisto's diameter of roughly 4,821 kilometers placing it in the same general class. Both orbit Jupiter. Both formed from similar raw materials in the same region of the solar nebula roughly 4.5 billion years ago. Both are composed primarily of rock and ice. On paper, they look like siblings. In reality, they could hardly be more different. Callisto appears to be only partially differentiated, or possibly not fully differentiated at all. Its moment of inertia, a measure of how mass is distributed within a body, suggests that its interior may consist of a relatively uniform mixture of rock and ice, without the clean, layered separation that defines Ganymede's internal structure. There may be a gradual increase in rock density toward the center, but nothing resembling the sharp boundaries between a metallic core, a rocky mantle, and an icy shell that Ganymede possesses. Some models suggest Callisto may have a small rocky core, but the evidence is ambiguous, and the 2026 study on Ganymede's core noted that non-hydrostatic effects could have inflated Callisto's measured moment of inertia, leaving the question of whether it has any metallic core at all genuinely open. Callisto shows no evidence of an intrinsic magnetic field. No dynamo operates inside it. Its surface is ancient, heavily cratered, and shows no signs of the tectonic resurfacing that created Ganymede's grooved terrain. Callisto's surface is among the most heavily cratered in the entire solar system, a testament to billions of years of impact accumulation, with no internal process ever erasing or overwriting the record. Where Ganymede replaced two-thirds of its surface with younger, tectonically shaped terrain, Callisto replaced none. Its face is a nearly perfect log of every collision it has endured since the heavy bombardment era, unmarred by any evidence that the interior ever exerted force on the surface. Why did Ganymede differentiate and Callisto did not? This question is one of the most debated in planetary science, precisely because the two moons seem so similar in their starting conditions. Both formed in the Jovian system, both had access to similar abundances of rock and ice, both experienced Jupiter's gravitational influence, but Ganymede is larger. Its greater mass meant that the accretion process generated more heat as material compressed under its own gravity. Ganymede may also have accreted faster, trapping more of that heat before it could radiate away into space. And critically, Ganymede participates in the Laplace resonance with Io and Europa, which provides ongoing tidal energy. Callisto orbits outside this resonance. It does not experience the same rhythmic gravitational flexing that supplements Ganymede's internal heat budget. The result is a threshold effect. Ganymede crossed the thermal line needed to melt its interior and allow gravitational separation. Callisto did not. One moon reorganized itself into a planet-like layered world. The other remained an undifferentiated mixture, geologically silent, internally primitive. Two moons, similar raw materials, similar ages, similar neighborhoods, radically different outcomes, separated by a margin of heat that made all the difference between a world and a lump. The comparison isolates the variable that matters most. Size and energy determine what an object becomes. Ganymede had enough of both. Callisto did not, and the solar system filed both of them under the same word. Io, the innermost Galilean moon, introduces yet another contrast. Io is the most volcanically active body in the solar system, with hundreds of active volcanoes driven by extreme tidal heating from Jupiter's gravitational influence. Io's surface is constantly being resurfaced by lava flows and volcanic deposits, making it one of the youngest surfaces in the solar system despite orbiting the oldest planet. But Io has no ice shell, no subsurface water ocean, no intrinsic magnetic field, and a composition dominated by silicate rock and sulfur rather than water and ice. Io is violently active, but narrow in the range of its complexity. It does one thing, volcanism, at an extraordinary level. Ganymede does many things: magnetic field, ocean, differentiated interior, tectonic resurfacing, surface chemistry, at a more moderate but far broader level. Earth's moon provides the starkest comparison of all, because it is the object that most thoroughly defines the mental category. Earth's moon is geologically dead in the present epoch. Its interior cooled enough that any ancient dynamo shut down billions of years ago. It has no global magnetic field. It has no atmosphere beyond the thinnest possible exosphere. It has no liquid water anywhere, surface or subsurface, beyond trace amounts of ice in permanently shadowed polar craters. Its surface has not been significantly resurfaced by internal processes in over 3 billion years. The Maria, the dark basaltic plains visible to the naked eye, represent ancient lava flows that ceased when the interior cooled. Earth's moon is the archetype of what people mean when they say moon, and it shares almost nothing in common with Ganymede beyond the orbital classification. If you placed Ganymede and Earth's moon side by side and asked which object deserved the label moon, the answer would seem obvious based on physical characteristics. Earth's moon looks like a moon. It is small, grey, cratered, dead, and dependent. Ganymede looks like a world. It is large, layered, active, magnetically shielded, and hydrologically complex. But the classification system does not care about physical characteristics. It cares about orbital relationships. Both objects orbit a planet. Therefore, both are moons. The word applies equally to an object with a 100-kilometer deep ocean and an active magnetic dynamo, and to an object that has been geologically inert for 3 billion years. The category is that blunt. This is where the comparison with Mercury returns one final time, not to repeat the size numbers established earlier, but to highlight a structural irony. Mercury is classified as a planet because it orbits the Sun independently. Ganymede is classified as a moon because it orbits Jupiter. But the reason Ganymede orbits Jupiter rather than the Sun is not that Ganymede is too small or too simple to be independent. It is that Jupiter is too massive and too gravitationally dominant for anything in its vicinity to have escaped its influence during the formation of the solar system. Ganymede did not fail to become a planet. It was captured by a planet so large that independence was never an option. Had Ganymede formed in an independent orbit around the Sun, at a distance where water ice could persist, it would be classified as a planet today. Not a major planet, not something rivaling Earth or Mars in mass, but a planet nonetheless. A world in its own right with a name and a status and a place in the public imagination far above its current position as one of Jupiter's moons. The only thing that prevented this outcome was gravitational geography. Ganymede formed in the wrong neighborhood. And the reason that neighborhood produced a world this complex is itself part of the story. When the solar system was forming roughly 4.5 billion years ago, the Sun was surrounded by a vast disk of gas and dust called the protoplanetary disk. Within that disk, material gradually accumulated into clumps, then into bodies, then into planets. The process was accretion, the slow aggregation of matter through collision and gravitational attraction. Every rocky planet in the inner solar system, Mercury, Venus, Earth, and Mars, formed through this process. Jupiter formed through the same process but on a larger scale, accumulating so much gas that it became a giant. And here is the detail that matters. As Jupiter grew, it developed its own miniature version of the Sun's disk. A swirling ring of gas and dust called a circumplanetary disk surrounded the young Jupiter, fed by material flowing inward from the larger solar nebula. Within this smaller disk, the same accretion physics that built planets around the Sun built moons around Jupiter. Material collided, compressed, and accumulated. Gravity pulled clumps together. Heat from compression and radioactive decay warmed the interiors. The process was physically identical to planet formation. The only difference was the address. Instead of orbiting the Sun, these objects orbited Jupiter. Ganymede formed inside this circumplanetary disk, the same way Earth formed inside the protoplanetary disk. The physics was the same. The raw materials were different, more ice and less iron at Jupiter's distance from the Sun. But the mechanism of accumulation, heating, differentiation, and structural organization was indistinguishable from how planets are built. Jupiter's disk was a factory for worlds that happened to orbit a planet instead of a star. It did not produce debris. It did not produce rubble. It produced differentiated, layered, magnetically active bodies with metallic cores and vast hydrospheres. It produced worlds, and then the language we use called them moons. This is the deepest layer of the gravitational geography problem. Ganymede did not form through a lesser process than planets. It formed through the same process, in a smaller disk, around a larger host. It is a planet formation product living at a moon classification address. The physics does not know the difference. Only the vocabulary does. ESA's JUICE mission, launched aboard an Ariane 5 rocket in April of 2023, is currently in transit toward Jupiter. The spacecraft completed a flyby of the Earth-Moon system in August of 2024 and a flyby of Venus in August of 2025. It is scheduled for a second Earth flyby in September of 2026 and a final Earth flyby in January of 2029 before arriving at Jupiter in July of 2031. After a series of flybys of Europa and Callisto, JUICE will enter orbit around Ganymede, becoming the first spacecraft in history to orbit a moon other than Earth's own. The mission carries a suite of instruments specifically designed to answer the questions that Ganymede's complexity has raised over the past 3 decades. The Radar for Icy Moons Exploration, referred to as RIME, will send radar pulses through the ice shell to probe its internal structure, potentially detecting the boundary between solid ice and liquid ocean. This instrument can penetrate ice to a depth of roughly 9 kilometers, not deep enough to reach the ocean directly, but sufficient to reveal layering, fractures, and structural features within the upper ice shell that would tell scientists how the ice behaves and whether liquid water pockets exist at shallower depths. The Ganymede laser altimeter, referred to as GALA, will map the surface topography with precision sufficient to detect tidal bulges. Ganymede's ice shell, if it floats on a liquid ocean, should flex in response to Jupiter's gravity as the Moon moves along its slightly eccentric orbit. The amplitude of that flexing directly constrains the thickness of the ice shell and the depth of the ocean below. A larger tidal bulge means a thinner, more flexible ice shell. A smaller bulge means a thicker, more rigid one. GALA will measure these deformations to within centimeters, converting the subtle breathing of the ice surface into hard numbers about what lies beneath. A magnetometer will map Ganymede's intrinsic magnetic field in three-dimensional detail, revealing whether the dynamo structure is simple or complex, symmetric or irregular. By measuring how the field changes at different altitudes and orbital positions, scientists will be able to constrain the size and composition of the core producing it. Simultaneously, the magnetic data will be used to study the ocean's conductivity through magnetic induction. When Jupiter's field changes around Ganymede, the response of the Moon's own field reveals the electrical properties of the conducting layer beneath the ice. Saltier ocean, stronger response. Thinner ice shell, faster response. The magnetometer will read the ocean's signature through the ice the same way Hubble read the auroral wobble, but with far greater precision and spatial resolution. Cameras and spectrometers will image the surface at resolutions high enough to identify individual cryovolcanic features, map the distribution of salts and organics, and assess whether specific geological features are active or dormant. Gravity science instruments will measure the distribution of mass inside Ganymede, detecting variations that reveal the boundaries between core, mantle, ocean, and ice shell. Each instrument attacks a different facet of the same fundamental question: what is Ganymede really? And each instrument's answer will make Ganymede feel less like a moon and more like a world. The fact that an entire flagship mission, one of the most ambitious deep space endeavors in European space history, is dedicated primarily to studying a moon tells its own story. Space agencies do not build multi-billion-dollar spacecraft to study objects that are merely interesting footnotes. They build them to study worlds. And the scientific community has quietly acknowledged what the classification system has not. Ganymede is a world. It has been treated as a world in research planning, in mission architecture, and in scientific prioritization for years. The mission to orbit it is designed with the same rigor and ambition that previous generations applied to Mercury, Venus, and Mars. When JUICE arrives and begins its orbital survey, the data it returns will almost certainly deepen every feature of the picture already established. The magnetic field will be mapped in three-dimensional detail. The ice shell will be measured for thickness and internal layering, potentially confirming or refining the stacked ocean model. The surface will be imaged at resolutions high enough to identify individual cryovolcanic features and assess whether they are active or dormant. The ocean's depth and salinity will be constrained by gravity measurements and magnetic induction studies. Each new data point will make Ganymede feel more planet-like, more structured, more substantial. And still, after all of this, the word applied to it will remain moon. The question is not whether the word is wrong. Ganymede orbits a planet. The word is correct. The question is whether the word is adequate, whether a single syllable that also describes Phobos, a captured asteroid barely 22 kilometers across that orbits Mars, can meaningfully describe an object with an active magnetic dynamo, a 100-kilometer deep ocean, a differentiated interior with a metallic core, surface salts deposited by deep ocean brine, candidate cryovolcanic vents, and a diameter exceeding the planet Mercury. The same word covers both objects, and that is the problem. The problem is not a failure of science. The taxonomy works perfectly well for orbital mechanics. The problem is a failure of language to match the reality it describes, and that failure has consequences for how people think about the solar system, how they prioritize exploration, how they allocate attention, and how they feel about objects that carry the diminishing label of moon rather than the elevating label of planet. The word shapes perception, and perception determines which objects feel like they matter. Ganymede matters. It matters in ways that the word assigned to it does not even begin to communicate. But understanding why it matters, understanding what the category collapse truly means, requires stepping back from the comparisons entirely and confronting the deeper truth about what Ganymede reveals, not about itself, about the idea of a moon. In 1610, Galileo Galilei pointed a crude refracting telescope at Jupiter and saw 4 points of light moving in formation around the planet. He did not know what they were. Nothing in the scientific framework of his era could account for small objects orbiting a world other than Earth. The prevailing model, the Ptolemaic system, placed Earth at the centre of all celestial motion. Everything orbited us. The idea that another planet could have its own retinue of companions was not just unknown. It was structurally incompatible with how educated people understood the cosmos. Galileo observed the 4 points of light over several nights, tracked their changing positions, and concluded that they were satellites of Jupiter. The word satellite did not carry the meaning it does today. It came from the Latin for attendant or escort. Galileo was describing objects that attended Jupiter the way courtiers attend a king. The metaphor embedded a hierarchy from the very beginning. Jupiter was the principal. These objects were the entourage. Around the same time, the German astronomer Simon Marius independently observed the same 4 objects and eventually proposed the names still used today: Io, Europa, Ganymede, Callisto. The names came from figures in Greek mythology, all of them lovers or companions of Zeus, the Greek equivalent of Jupiter. Even the naming convention reinforced the subordinate relationship. These objects did not receive names that implied independence or sovereignty. They received names that implied romantic attachment to a more powerful figure. They were defined by their relationship to Jupiter from the moment they were christened. 4 centuries later, nothing fundamental has changed about how the word moon positions these objects in the human mind. A moon is still understood as an attendant, a follower, a body whose identity derives primarily from the thing it orbits, rather than from what it is in its own right. When someone says Ganymede is one of Jupiter's moons, the sentence performs a grammatical act that most listeners do not notice. It makes Ganymede a possessive, something that belongs to Jupiter, Jupiter's moon. The phrasing strips agency, strips independence, strips individual identity. It files Ganymede inside Jupiter the way a chapter is filed inside a book. The chapter exists only as a component of the larger work. This linguistic framing is not accidental, and it is not neutral. It shapes how people allocate attention, curiosity, and emotional significance. Say the word Mars and a listener imagines a distinct world, red and dusty, with canyons and volcanoes, a place that might one day host human footprints. Say the word Ganymede and a listener imagines, if they imagine anything at all, a vague icy sphere trailing behind Jupiter. The first word opens a door to a world. The second word closes the door before the listener even thinks to look through it. The disparity has nothing to do with what the objects actually are. It has everything to do with the category assigned to them. Planet is a word that invites exploration. Moon is a word that suggests the exploration has already been done by studying the planet. But Ganymede did not agree to be minor. Its metallic core kept convecting. Its magnetic field kept generating. Its ocean kept existing, 100 kilometers deep, sealed beneath ice, holding more water than every ocean on the world where the word moon was invented. Its surface kept recording tectonic stresses and briny deposits from an interior that refuses to go quiet. And every feature it developed made the word assigned to it feel slightly less accurate, not as a matter of orbital mechanics, but as a matter of what the word communicates to the human beings who use it. This is the distinction that matters. Ganymede is a moon. That is an orbital fact. It orbits Jupiter. Jupiter orbits the Sun. The classification is correct and will remain correct regardless of what Ganymede does internally, how large it grows relative to other objects, or how many planet-like features it accumulates. No amount of magnetic field strength or ocean depth will change the orbital relationship. Ganymede will not suddenly begin orbiting the Sun independently. The taxonomy holds. What does not hold is the emotional and conceptual content that the taxonomy delivers to anyone who encounters it. The classification says moon. The human mind hears small, simple, secondary, and the object itself contradicts every word of that translation. This is not a scientific problem. It is a language problem, and language problems have real consequences for how civilizations prioritize the study and exploration of their own cosmic neighborhood. There is a historical irony buried in this problem that goes deeper than most people realize. The Copernican revolution, the great intellectual upheaval that removed Earth from the center of the cosmos and placed the sun there instead, is rightly celebrated as one of the most important shifts in human thought. Before Copernicus, Earth was the center of everything. After Copernicus, Earth became one world among several orbiting a star. The shift was humbling, liberating, and scientifically transformative. It taught humanity that our planet is not special by position, that the universe does not revolve around us, and that other worlds exist in their own right. But the Copernican revolution did something else that nobody talks about. It accidentally elevated planets to the only category of world that matters. In the Ptolemaic system, there were no moons. Everything orbited Earth. There was no secondary category, because there was no primary one. When Copernicus recentered the cosmos around the sun, he created a new hierarchy. Objects that orbit the sun became planets. Objects that orbit planets became something lesser. The word moon inherited a built-in demotion the moment the heliocentric model was accepted. Planets were promoted to the status of worlds. Moons were demoted to the status of companions. And that demotion has persisted, unexamined, for 5 centuries. The irony is that the Copernican revolution succeeded in decentering Earth, but failed to decenter the concept of planet. It taught people that Earth is not the most important place in the solar system, but it replaced that error with a subtler one, the assumption that only planets are important places. Moons became, by definition, secondary, not because anyone examined their properties and found them unworthy, but because the intellectual framework that replaced geocentrism had no room for a moon that deserved the same attention as a planet. The hierarchy was baked into the model from the beginning, and it has shaped how every generation since has thought about the solar system. Ganymede breaks this inherited hierarchy, not by ceasing to be a moon, but by being so obviously world-like that the hierarchy stops making emotional sense. If the Copernican revolution was about decentering Earth, Ganymede's lesson is about decentering the planet as the only kind of world worth caring about. The solar system contains worlds at every level of the gravitational hierarchy. Some of them orbit stars. Some of them orbit other worlds. The orbital address does not determine the complexity of the object living there. Consider how funding, missions, and public attention distribute across the solar system. Mars has received more spacecraft visits than any planet other than Earth. Multiple rovers have driven across its surface. Orbiters have mapped it in extraordinary detail. Entire career paths in planetary science are built around Mars research. Venus, despite being closer to Earth and roughly similar in size, receives far less attention, partly because its surface conditions are hostile, but partly because Mars occupies a larger space in the cultural imagination. It feels like a destination. Jupiter and Saturn receive attention as planets, the giant worlds that anchor the outer solar system. Their moons receive attention primarily as accessories to the planetary story, environments worth studying because they orbit interesting planets. Ganymede, despite possessing a suite of features that individually rival or exceed those of Mercury, despite harboring an ocean that may contain more water than all of Earth's surface water combined, despite generating the only dynamo-driven magnetic field of any moon in the solar system, receives a fraction of the attention directed at Mars. Not because it is less interesting, not because it is less scientifically valuable, but because the word moon places it in a perceptual category that implies it is less important. The word did that, the word alone. ESA's JUICE mission, which will orbit Ganymede beginning in the early 2030s, represents the first time a spacecraft will orbit any moon other than Earth's own. That fact should stagger anyone who pauses to consider it. Humanity has been launching spacecraft for nearly 70 years. We have orbited Mercury, Venus, Mars, Jupiter, Saturn, and even a comet. We have landed on Titan's surface and dropped a probe into Jupiter's atmosphere. Yet in all that time, no mission has ever established orbit around one of the hundreds of moons populating the solar system, except our own. Ganymede will be the first, and the reason it took this long is not that the technology was unavailable. It is that moons, as a category, did not command the priority that planets did. The word determined the schedule. When JUICE enters orbit around Ganymede, The data it returns will do something that no previous mission has done. It will describe a moon the way previous missions describe planets. It will map the magnetic field in 3 dimensions. It will measure the ice shell thickness. It will constrain the ocean depth and salinity. It will image the surface at resolutions sufficient to identify geological features and assess activity. It will study the exosphere, the magnetospheric interactions, the gravity field, the internal mass distribution. The resulting portrait will be the most detailed characterization of any moon other than Earth's ever produced, and the portrait will look like a planet. This is not speculation. Every previous increment of data has pushed Ganymede further in the planet-like direction. Galileo discovered the magnetic field in 1996, and the object became more planet-like overnight. Hubble revealed the suppressed auroral rocking in 2015, confirming the subsurface ocean, and Ganymede became more planet-like again. Juno detected salts and organic compounds on the surface in 2021, and the picture sharpened further. A 2026 study proposed that the core may still be actively forming, adding another layer of dynamism. Every new observation adds a feature that belongs on a planet rather than a moon. The trajectory is unidirectional. Ganymede only becomes more world-like as the resolution increases. It never retreats toward simplicity. And this raises a question that extends far beyond Ganymede. If one moon in our solar system can be this large and this complex, how many more objects in the universe have been dismissed by the same word? The solar system alone contains at least 6 moons with confirmed or strongly suspected subsurface oceans: Europa, Ganymede, Callisto, Enceladus, Titan, and possibly Triton. Some of these may harbour conditions suitable for biology. Several possess geological activity in the present epoch. At least one, Ganymede, generates its own magnetic field. These are not minor objects. They are worlds by any functional standard. Yet all of them carry the same label, the same diminishing syllable, the same categorical assignment that tells the human brain to rank them below the planets they orbit. The exoplanet era makes this problem not merely more acute, it makes it potentially the largest blind spot in how humanity thinks about habitable worlds. Over the past 3 decades, astronomers have confirmed the existence of more than 5,000 planets orbiting other stars. A significant fraction of these exoplanets are gas giants, objects comparable to Jupiter and Saturn in mass and composition. Many of them orbit within or near the habitable zones of their host stars, the range of distances where temperatures permit liquid water on a surface. These gas giants are almost certainly not habitable themselves. They are vast spheres of hydrogen and helium, with crushing atmospheres and no solid ground. But their moons might be. If those gas giants have moon systems anything like Jupiter's, and the physics of planetary formation strongly suggests they should, then the galaxy contains not merely billions of moons, but billions of moons orbiting within habitable zones. Some fraction of those moons will be Ganymede-scale objects or larger. Some will be tidally heated by their host planet. Some will possess subsurface oceans warmed by the same resonance-driven flexing that sustains liquid water on Europa and Ganymede. Some will have magnetic fields protecting their surfaces from stellar radiation. Some will have atmospheres thick enough to retain warmth and weather. The implication is staggering and still largely unexamined in public discourse. The most common habitable worlds in the galaxy may not be planets at all. They may be moons. Rocky Earth-like planets in habitable zones appear to be relatively rare based on current exoplanet surveys. Gas giants in habitable zones are far more common. If each gas giant hosts even a few large moons, the total number of potentially habitable moons in the galaxy could vastly exceed the number of potentially habitable planets. The search for life beyond Earth may ultimately depend not on finding another Earth, but on finding another Ganymede. Another world with a subsurface ocean, a magnetic field and active chemistry, orbiting a gas giant that provides the tidal energy to keep the interior warm. And yet, every single one of those objects, every potentially habitable moon in every star system in the galaxy, will be described by a word that tells the listener it is less important than the planet it orbits. The cognitive trap is not local, it is universal. The word moon does not merely diminish Ganymede, it diminishes every world-like satellite in existence, everywhere, around every star, across the entire observable universe. The hierarchy baked into the language of astronomy 5 centuries ago scales to a cosmic problem. The most common habitable worlds may be the ones our vocabulary was designed to overlook, and there is a final twist that makes the problem complete. Not only has the language hidden these worlds from human attention, the physics has hidden them from human instruments. As of today, no exomoon, not a single moon orbiting a planet in another star system, has been definitively confirmed. There are candidates. A handful of signals detected by the Kepler Space Telescope and other surveys hint at the presence of large moons orbiting gas giants in distant systems, but none has been verified beyond reasonable doubt. The signals are too faint, too ambiguous, too entangled with the signals of their host planets to separate cleanly with current technology. The reason is fundamentally geometric. When astronomers detect exoplanets, they typically use the transit method, watching for the tiny dip in starlight that occurs when a planet passes in front of its host star. The dip is small, often less than 1% of the star's brightness, but detectable with sensitive instruments. A moon orbiting that planet would produce an even tinier dip, a signal within a signal, and its timing would shift from transit to transit as the moon moves along its own orbit. Detecting this requires not just sensitivity, but the ability to distinguish the moon's contribution from noise, stellar variability, and the planet's own signal. For a Ganymede-sized moon orbiting a Jupiter-sized planet, the additional dip would be roughly 700 times smaller than the planet's transit signal. Current instruments are at the very edge of this detection threshold. The next generation of telescopes may cross it. The irony is precise. The objects that may represent the most common habitable worlds in the galaxy are also the hardest to detect. They are hidden behind their host planets photometrically, buried in noise statistically, and dismissed by the word moon linguistically. The invisibility is triple layered. The instruments cannot quite see them. The data cannot quite confirm them. And the vocabulary, even if they are found, will immediately file them into the category that tells people not to care. This is where the category stops being a neutral label and starts becoming a cognitive trap. The word moon does not merely describe an orbital relationship. It tells the listener how to feel about the object. It tells them the object is subordinate, derivative, dependent. It tells them the real story is the planet, and the moon is a footnote. Every child who learns the solar system absorbs this ranking without being explicitly taught it. The hierarchy is embedded in the language itself. Planets are destinations, moons are details. And the language persists even when the details turn out to be more remarkable than the destinations. Ganymede's existence forces a confrontation with this hierarchy, not because Ganymede needs to be reclassified. It does not. The orbital definition is clear and serviceable, but because Ganymede reveals the gap between what the word communicates and what the object contains, that gap is not small. It is the difference between imagining a frozen rock trailing behind a gas giant and imagining a layered world with a liquid iron core, an active magnetic dynamo, auroral ovals glowing at both poles, a saltwater ocean deeper than any abyss on Earth, mineral salts and organic compounds scattered across a surface that may still be venting material from the deep interior, and a geological history that includes tectonic resurfacing across 2/3 of its terrain. The word moon contains all of that, and it communicates almost none of it. The real shock of Ganymede is not that it is larger than Mercury, although it is. The real shock is not that it has a magnetic field, although no other moon does. The real shock is not the ocean, the salts, the organics, the auroras, the candidate cryovolcanic vents, or the ongoing core formation. The real shock is that all of these features exist inside an object that most people will never think about because the word attached to it told them it was not worth thinking about. And the deepest layer of that shock is this: Ganymede is not the exception, it is the revelation. It reveals that the category of moon is far larger, far more varied, and far more capable of containing world-like complexity than most people have ever been led to believe. Ganymede is the most extreme case, the largest and most complex moon in the solar system. But it sits at the top of a spectrum that includes Titan with its methane lakes and thick atmosphere, Europa with its thin ice and promising ocean, Enceladus with its geysers erupting water vapor into space, and Triton with its retrograde orbit and nitrogen geysers. These objects are not footnotes, they are worlds. Some of them may be the most important places in the solar system for the question of whether life exists beyond Earth. And the word applied to all of them is the same word applied to Phobos, a misshapen fragment of rock too small to even pull itself into a sphere. The word moon does not distinguish between these objects. It flattens them. It takes a spectrum of complexity, ranging from captured rubble to differentiated worlds with oceans and magnetic fields, and compresses it into a single syllable that carries connotations of smallness and dependence. This is what Ganymede breaks, not the definition, the connotation, the assumption, the quiet, unexamined belief that a moon is a minor thing. That belief was always wrong. Ganymede simply makes the wrongness impossible to ignore. Imagine, for a moment, that you could strip Ganymede away from Jupiter, slide it gently out of its orbit, slow it down, and place it in an independent path around the Sun at a distance where its ice would remain stable but sunlight would illuminate its surface clearly. Remove the gravitational context that classifies it as a moon and let it stand alone. What would you see? You would see a world 5,268 kilometers across, wider than Mercury, with a surface divided between ancient cratered highlands and younger tectonically reshaped terrain. You would detect a magnetic field generated by an internal dynamo, something that many planets in the solar system cannot claim. You would identify a subsurface ocean of liquid salt water estimated at 100 kilometers deep, potentially the largest subsurface ocean yet identified in the solar system. You would find salts and organic molecules on the surface, chemical remnants of an interior ocean that communicates with the frozen exterior. You would observe auroras at both poles, luminous evidence of a functioning magnetosphere. You would study a differentiated interior with a metallic core, a rocky mantle, and a complex ice and water shell hundreds of kilometers thick. You would call it a planet. Without hesitation, without debate, without any lingering sense that the object was too small or too simple to deserve the word. Everything about it would read as planetary. The size, the structure, the activity, the complexity, the ocean, the magnetic field, the surface chemistry. If Ganymede orbited the Sun, textbooks would feature it prominently. Documentaries would explore it in detail. Children would learn its name alongside Mercury, Venus, Earth, and Mars. It would be treated as a world. But Ganymede does not orbit the Sun. It orbits Jupiter. And that single fact, that accident of gravitational geography, seals it inside a word that hides almost everything it actually is. The word moon sits on Ganymede, the way a dust cover sits on a grand piano. The instrument underneath is extraordinary. The cover makes it look like furniture, and here is where the story arrives at its final point. Ganymede does not break the definition of a moon, it breaks the idea of a moon. The definition is orbital and mechanical. It works fine. The idea is emotional and perceptual. It does not work at all. The idea says moons are small, Ganymede is larger than a planet. The idea says moons are simple. Ganymede has a layered interior with an active dynamo. The idea says moons are dead. Ganymede's core may still be forming. Its ocean may still be leaking brine to the surface. And its magnetic field is operating right now. The idea says moons are secondary. Ganymede is the primary scientific target of one of the most ambitious space missions ever launched. Every element of the common idea of what a moon is supposed to be fails when applied to Ganymede. And because Ganymede is not an anomaly but rather the most extreme member of a spectrum that includes dozens of complex, active, world-like moons throughout the solar system, the failure extends far beyond a single object. The failure belongs to the idea itself. The idea that moons are minor. The idea that the word moon tells you what kind of object you are dealing with. The idea that a label assigned based on orbital mechanics communicates anything meaningful about what an object is, what it does, or what it contains. Ganymede contains a metallic core that generates a magnetic field no other moon produces. It contains a saltwater ocean 100 kilometers deep, pressurized beneath ancient ice, a body of liquid water so vast it has no equivalent anywhere on the surface of any planet. It contains a geological record of tectonic resurfacing driven by internal forces. It contains surface chemistry deposited by processes that reach from the deep ocean floor through 150 kilometers of ice to the frozen ground above. It contains an ongoing story of internal activity, of a core potentially still under construction, of a dynamo still running, of a world still evolving beneath a surface that looks, to the casual observer, like nothing more than grey ice. And the solar system placed all of this inside an object and called it a moon. The real shock was never that Ganymede is large. The real shock was never that it has features that rival or exceed a planet. The real shock is what Ganymede reveals about the size of the word we use to contain it. The word moon is supposed to hold everything from captured asteroids to differentiated worlds with 100-kilometer oceans and active magnetic dynamos. It is supposed to mean Phobos and Ganymede equally, and that is the problem. Not that the word is wrong, that the word is too small. It was always too small. Ganymede just made it obvious. Somewhere right now, 778 million kilometers from the Sun, a world wider than Mercury is orbiting a gas giant. Its iron core is convecting. Its magnetic field is holding. Its ocean is lying silent and vast beneath the ice. Its auroras are glowing faintly at both poles, rocking gently against the pressure of Jupiter's immense magnetism. Its surface carries the chemical fingerprints of a deep interior that will not stop reaching upward, and the word on its nameplate says moon. The word was never big enough. Ganymede just made sure you noticed.